you have heard me talking a little bit about the way this module is organised. We've got people here who are signed up for Embedded Systems Engineering, CM0605. We've also got people here who are signed up for Distributed Real-Time Systems, KF6010. The reason we're being taught together is because the content for both modules is the same. And it just depends at what stage you are through your program as to which one you've been registered on. So you'll see that the lecture slides typically come with a title for both modules and also with module numbers for both modules. So the idea in this session is just to introduce you to the module. Depending on how time goes, we might get into some more technical stuff as well. But the main point of the session is just to introduce the module. And the way in which I typically do that is really just to take the titles of the modules and break them down a bit. So we've got one title as Embedded Systems Engineering. So I'm going to say a little bit about embedded systems, and I'm going to say a little bit about engineering. And the other module title is Distributed Real-Time Systems. So I'll say a little bit about what we mean by distributed, and a little bit about what we mean by real-time. And we'll try and put those ideas together so that you go away knowing what we mean by embedded systems engineering, what we mean by a distributed real-time system, and how the module is going to address those issues. Is that okay? So let's start off with thinking a little bit about embedded systems and what kinds of embedded systems we might be interested in. This photo's starting to show its age a little bit now. So it's a photo of a car seat from an automotive electronics show, which would be great, but it was taken in 2004. But it still allows me to illustrate the main point. We've got a single car seat here. We might wonder how many CPUs there are just in this one car seat. When we have a look at that, we'll see in this particular seat there are 4 CPUs. There's one for front and back motion, another one which controls the tilt of the seat, another one for lumbar support, and also a control button interface. So we've got this one kind of standard bit of equipment in our car, and already we've got 4 ECUs, 4 small embedded systems in the car seat. And the thing that makes it embedded is there's some control aspect. It's there's something to control some part of the physical environment. So this is a computer embedded in a physical environment. We've got 4 of them in one of our car seats. You might ask, how many are there in a car? Well, I'm not, you'll be pleased to hear, going to work my way around this diagram and count up how many there might be. The numbers vary. So according to the slide, again, the slide is a little bit out of date. 10 years ago, a Mercedes S-Class car had at least 70 networked ECUs. You can update that. It hasn't grown as much as you might think, but a typical modern car will have probably over 100 ECUs in it. So your car is a kind of canonical example of the kind of systems that we're interested in. It's got multiple ECUs. As we'll see in a moment, the ECUs are connected by some kind of communications network. So here's a kind of abstract view of the structure of the embedded systems in our car. And you can pick out some of the key communication technologies here. Here there's a CAN bus, controller area network. There's a kind of cheap and cheerful version of CAN called LIN, which is a local interconnect network, which is used for less critical systems. And if you have a look around, you can see several of those. A CAN bus here, another LIN bus here. And they're joining together the instrument panels, the climate control, the lights, the seating, some work on the drivetrain, the steering, and so on. So if you're looking for a canonical example or a paradigm of the kind of systems that we're interested in, your car provides that for you. We've got these embedded systems, little computers embedded in the environment, controlling or providing information about some aspect of the environment. The thing that makes these systems distributed is the fact we've got multiple microcontrollers, and they're connected by some communication mechanism. And they communicate with each other, and the intention is that they fulfill some overall function. So, for example, it might well be that some element of the drivetrain communicates with some element of your audio system, so that depending on your speed and the road surface noise, the volume of your audio system can be adjusted. So different components communicate with each other so that they can cooperate to provide a satisfactory function. So that's all we mean by distributed. The processing is distributed over a number of computing nodes. Sometimes we'll talk about a distributed system where it's some other resource which is distributed, maybe the memory. But typically we mean the processing resource is distributed over a number of different nodes. So that's an example from the car. This slide is just intended to widen that out a little bit. Actually, every time I look at the slide, though, I realise that they're all pretty much examples of some kind of transportation. So we've got jet engines, we've got the nose of an aircraft, we've got submarines, we've got, I think this must be the lifts in the Lloyd's building in London. We've got trains and so on. But the area is wider even than that. So you can think of medical control systems, manufacturing processing systems, all kinds of robotic systems and so on. They're all examples of embedded system, and typically they're all examples of a distributed real-time system. Yeah, if you had the pleasure of taking the embedded system specification and design, or the model base, whatever it is, I'm going to have to stop saying both module titles. Let's just stick with model-based design and verification for the moment. If you've just been in that module, you'll have seen this before. Actually, let me just get rid of that. Give me a quick run through the essential characteristics of an embedded system. I know some of you have already seen this slide this morning. So you've got 4 things to remember here.
Concurrency.
Perfect.
Communication.
Excellent.
Resource constraint.
Very good, Matt. At least somebody was paying attention. Yeah, okay. So concurrency, communication, real-time, and resource constraints. For those people who didn't come to the previous lecture, I'll briefly run through this again and tell you why these characteristics are important. So even if you've got an embedded system just with a single node, the chances are that you've got some multitasking going on that single node. If you've got a distributed system, you've got multiple nodes, certainly you've got concurrency in that case. But you'll you'll only infrequently come across an embedded system which doesn't provide you with the challenge of dealing with some kind of concurrency. In a distributed system, in order for nodes to be able to cooperate, they have to communicate with each other, either to provide control signals or to receive data. So there's some communication going on. The timing requirements are established by the environment. So if you've got a database system, then to some extent the timing requirements are established by the environment. So if you've got the back end of your Amazon shopping window, if you click on a link to a page and it goes off to retrieve some data from the database, if you're waiting for more than a second, you're probably irritated. But at least you're not dead. If you're waiting for 5 seconds, you're still not dead. Even if you have to go off and make a cup of coffee while your page loads, you're still not dead. But if you've got a system where you press the brake pedal of your car and the brakes don't activate for 5 seconds, somebody probably is dead. So the environmental demands establish the timing requirements. So it's not the timing requirements aren't set by the control system that you're building. The timing requirements come from the necessity to interact with the environment in a timely way. So that's what makes our systems real time. Almost always the environment is imposing some constraint on us to provide some response within some tight time period. And the final point, the resource constraints. We're typically dealing with limited resources. So if a manufacturer can send out a product with a cheaper processor or less memory or a smaller battery or less powerful peripherals, they'll do that because it saves them money. So if you've got a run of 10 million units of some particular product, and you can save 50 pence per unit, then you've saved your company £5 million. So the pressures are always there to reduce costs, and typically costs are reduced by reducing the resources that you've got. So almost always you're dealing with some significant resource constraints. So these are the key characteristics of the embedded systems, and therefore the distributed real-time systems that we're interested in. Okay, so that's embedded systems, and I'll come back to distributed and real-time in a little bit more detail later. Let's just think about engineering for a moment. When I was looking for definitions of engineering, the one which seemed to me to be the closest to my own view was one from the American Engineers Council for Professional Development. It's a bit of a mouthful. So they define engineering as the creative application of scientific principles to design or develop structures, machines, apparatus, blah blah blah, etc., etc., etc. I'm going to break this mouthful down into its component parts, rather than stand here and read it out to you. When you break it down and you try to apply it to embedded systems, it comes down to this. It's about the application of scientific principles to the design of embedded systems, to the construction of embedded systems with full cognizance of their design. You can see that's taken directly from this mouthful over here. Construct or operate the same with full cognizance of their design. Or to forecast their behavior under specific operating conditions. The forecasting of the behavior of embedded systems under specific operating conditions. And we're doing this with respect to their intended function with respect to the economics of operation and with respect to the safety to life and property. So we're applying scientific principles to the engineering of embedded systems, to ensuring that we're completely aware of all of the implications of the design, and to the forecasting of their behaviour under specific operating conditions. That means it's not good enough to knock something together and then stick it into the environment and see if it works. As I said a lot in the last lecture, we need probably to build some models. We need to do some analysis. We need to be employing well understood implementation techniques. Because very often the systems that we're dealing with are critical in some way. Either critical because their failure might lead to loss of life, or because they might lead to loss of money or reputation. So, if we carry that through to what we saw about the essential characteristics of an embedded system, then we're trying to apply scientific principles to the design, construction, and analysis of systems that have those characteristics. So we want to be able to reason properly about concurrency, communication, real-time, and resource constraints. Okay, so let's just expand a little bit on those ideas. So concurrency arises when multiple processes share a single processor. It also arises when multiple nodes share a communication mechanism. Let's focus for the moment on multiple processes sharing a single processor. So, how is the processor allocated to our different tasks? Well, one possibility is that we allocate the processor on an event-triggered basis. So typically an event in our system is made known to the processor by an interrupt. So some interrupt occurs. In general, what we mean by an event-triggered system is one in which we'll accept interrupts from multiple sources. So maybe it's a periodic timer overflow that's caused the interrupt, or maybe a message has arrived on our CAN bus or from our Ethernet switch. Maybe we've pressed a switch somewhere on our system and that's caused some GPIO to raise an interrupt. Maybe we've asked for an analog to digital conversion somewhere down the line and that's just finished, and now we're ready to collect the data, and so our ADC raises an interrupt for us. We'll see in a moment, well, maybe in a moment, maybe it'll be next week, but we'll see shortly that the microcontrollers that we're going to be using for our practical work have a whole plethora, a whole variety of different sources of interrupt. So one possibility is that every time one of these interrupts occurs, something happens in our software to determine that some particular task gets to run. An alternative to that approach is to say we're only going to consider one source of interrupt, and that will be a timer. So we'll have some timer, usually periodically, firing off an interrupt, and at that point our software gets a chance to decide which tasks are going to run. Now, you can make an argument for both of these approaches to building your system. In the event-triggered case, it might be that you can be more responsive, at least for some of your crucial interrupts, but it may be much harder to reason about the behavior of your system in all possible circumstances. So if you're thinking about this issue of the construction of a system with full cognizance of their design and the ability to forecast behavior, then you might be pushed towards the time-triggered approach. But if you're trying to make your system responsive and perhaps make better use of resources, then maybe you push towards the event-triggered approach. So we've got some design choices to make. What you want to be able to do as an engineer is have an understanding of both of these major approaches so that it really is a choice for you. If you only understand one approach, then you'll never think to use the other approach. Whereas if you understand both, then it becomes a serious design choice for you, and you can pick the best approach for whatever system you're trying to build. So managing and reasoning about concurrency is a major challenge. If we've got a distributed system, then our computing nodes are going to communicate with each other in some way. And again, the economic and safe allocation of resources is going to require a predictable communication network. So this is back to this idea of engineering being able to forecast the behavior of your system before you deploy it. So typically, we don't worry too much about predictable communications. As long as our communications are good enough, then normally we're happy. Hence the prevalence of Ethernet everywhere. Can anybody remind me how nodes sharing an Ethernet network typically get access to the network? What's the, I think my question is concerned with what's the MAC protocol for Ethernet, the Medium Access Control Protocol? Have you heard of, does the term CSMA-CD ring any bells with anybody? Carrier sense multiple access with collision detection. Yes? No? Okay, well, let me briefly fill you in on how, roughly how Ethernet works, how it accesses the communication medium. So CSMA-CD, so let's just break this down. Carrier sense multiple access. So the multiple access part is easy. It means that all nodes connected to your network can try to access the network at any time. So if you've got multiple nodes connected to your Ethernet, any one of them can try to send a message at any time. Okay, so what's a potential problem with that? Collision, yeah, so if you've got two nodes simultaneously trying to send a message, then those messages might collide in the sense that one node will be trying to put one bit pattern onto the network, but the other node will be trying to put a different bit pattern onto the network. And that's going to, if that happens, then there's going to be some sort of horrible mess. So you need some mechanism to try to avoid that occurring. So the basic mechanism is the carrier sense part. So before a node is allowed to transmit, it tries to figure out if there's some other node currently transmitting. So it senses the carrier. So the carrier is just the physical medium. So it senses the carrier. If there's some other node trying to transmit, then it doesn't start its transmission yet. So it waits until the current transmission finishes. Okay, does that solve the problem completely? This is a yes or no question. I don't mind if I've got half of you saying yes and half of you saying no.
No.
It doesn't. Okay. Okay. Now that leaves you open to a follow-up question, unfortunately, Liam.
Is it because two nodes might try to transmit at the same time and they don't detect the carrier?
So that you've got two nodes who've got a message to transmit. They're both sensing the carrier. They both notice that the current message transmission has finished, so they detect at the same time that the carrier is free, and now they both try to transmit. Yeah. So you've still got the possibility of collision. So the CD part tells you how that collision is resolved, or at least what happens about that collision. So CD is collision detection. So the mechanism detects the fact that the collision has happened. Okay, so what then happens? What happens at that point is that all nodes stop transmitting and they back off for a random period of time. So each node which wants to transmit chooses a different, well, you hope it's going to be different, a different length of time that they're going to wait for before they try to transmit again. Yeah, so they both try to transmit. They've detected the collision, so they both think, oh, I'll put my feet up for a few seconds before I try to transmit again. They choose the back off time from some window of possible times available to them. There's just a chance that the nodes will choose the same period of time to back off for. So the next time they both start trying to transmit, again there'll be a collision. So if that happens, they choose a bigger time interval to choose their back off times from. So now there's less chance that they'll collide again. But if they do, they'll choose a bigger time, and so on. But the trouble with this approach for predictability is that we don't know how long any given node is going to back off for before it succeeds in transmitting its message. Yeah, so we don't have a basis for a predictable communication system. So if you wanted to put a network like that into your car and connect your brakes to it, probably nobody's going to be terribly happy, because somebody might be turning up the volume on their audio system, and those are the messages which are succeeding. A lot of the work involved in engineering a distributed real-time system or a distributed embedded system is work involved with predictable communication networks. So with CAN, Controller Area Network, you can do better than that. CAN has a similar approach to Ethernet, but we're going to look at the details of how CAN works in semester 2. Its approach to sorting out collisions is predictable. We've got a slightly different variant of CAN called TT-CAN, time-triggered CAN, which adopts, as you'd expect, a time-triggered approach to handling the access to communication. And more recently, there's been quite a bit of work on time-triggered Ethernet, which takes essentially an Ethernet approach, but it ensures that collisions don't arise because nodes are given a time slot in which they're allowed to transmit, and that avoids collisions. There's another bus which is getting a lot of attention currently in the automotive world called FlexRay. That kind of adopts a hybrid approach, if you like. So some messages are time triggered with guaranteed predictable delays, but some messages are allowed to be what you might call best effort, in which the need for predictability isn't strong, and so we can just make use of any remaining bandwidth in the network for sending our best effort messages. We're going to look at predictable communication in semester 2. In fact, this might be a good time to tell you a little bit about how the module is split. Semester 1 is essentially about techniques for building predictable uniprocessor systems, and we're going to show you a whole bunch of techniques that allow you to do that. We'll focus on event-triggered and time-triggered approaches. We'll look at a variety of approaches that either make use of an operating system or some that don't make use of an operating system. And for the approaches based on an operating system, we'll look at different types of operating system as well. We'll show you some analysis methods that you can apply to your implementations, so you can make predictions about the behavior of your uniprocessor systems. By the time you get to the end of semester one, you should have a whole tool bag of approaches that allow you to build a solid, predictable uniprocessor embedded system. And then in semester two, we'll look at the distributed aspects. So as far as predictable communication is concerned, we'll spend quite a bit of time looking at CAN, but we'll also look at some systems which have less strong requirements for predictability. We'll look at some Internet of Things type approaches, and so on. But the basic split between semester one and semester two is semester one essentially uniprocessor, semester two essentially distributed. A little bit about real time. I've said that the real time requirements come from the environment. The definition of real time, which has been used since the early 90s, is that a real time system is a system where the total correctness of an operation depends not just on the logical correctness of the result, but also on its temporal correctness. So until people started thinking about real time seriously, logical correctness was really the only correctness property of any concern. So normally our systems were sequential. You'd feed some inputs into your algorithm, and eventually you'd get some outputs out. And as long as the outputs were related to the inputs in some proper way, then you would say your algorithm was correct. So if for a given input you get the right output, everybody was happy. As soon as you've got a real-time constraint, though, it's not just logical correctness which is important. So we still need logical correctness. For a given input, we still need the right output, but we need the right output at the right time. And that's what we mean by temporal correctness. Yeah? So a real-time system is one where the overall correctness isn't just about logical correctness, it's about this combination of logical and temporal correctness. Very often our correctness properties will be expressed in terms of a deadline. It might be an absolute deadline, so maybe our operation needs to complete by 10:53 on the 2nd of October, or it might be some relative deadline. Within 10 milliseconds of this event occurring, some other event must occur. So possibly an absolute deadline, possibly a relative deadline. That might be the way in which we specify our temporal correctness. Okay, so that gets the idea of real time. There's an important classification of real time systems between hard real time and soft real time. If you think about the value that the system provides for you, depending upon the way in which your real-time requirements are met, then it might be that your system is either useless or possibly even it has a negative effect if your result isn't produced by its deadline. So we'd regard that as a hard real-time system. If there's even one deadline which isn't met, and that renders your system useless or means that it has a negative impact on the world, then that's a hard real-time system. On the other hand, it might be that you've got some deadlines that you would like to meet, but maybe it doesn't matter if you miss one, or even a few. As long as you don't miss too many, then the overall functioning of the system is still positive. So the classic example of that is video streaming. So when you're playing back a video stream, you've got some real-time requirements. The real-time requirement is that the next frame must be available for displaying to the viewer in time following the previous frame. And the time is kind of determined by the visual system of a human being. If you can detect some kind of flickering or gap or some visual disturbance on the display, then you haven't met your real-time requirement. But the visual system of the human being isn't fantastic. So it might well be that you can miss a frame, and as long as the next frame isn't too long following in, a human won't detect that the frame's been missed. So in that case, your video streaming is still of value. You still look as though you're seeing everything okay, and there are techniques to help make up for missing frames. So for example, if the next frame isn't available for display, maybe you'll just display the current frame again in that time slot. And as long as that doesn't happen too often, probably the human viewer won't be able to tell the difference. So we'd say that's a soft real-time system. There are some deadlines. Clearly, if there's a 5-minute gap between frames, then something has gone wrong. I know we've got buffering and so on, but let's ignore buffering for the moment. Clearly, if there's a 5-minute gap between frames, then something has gone seriously wrong. But if there's just occasionally a missed deadline, then probably we won't be able to tell the difference. So that would be a soft real-time system. So this is an important distinction between hard real-time and soft real-time. One in which a single missed deadline renders our system useless. One in which the occasional missed deadline probably doesn't matter too much. Yeah. The focus in this module is going to be on hard real-time. So most of the techniques that we look at are for building hard real-time. If you can build a hard real-time system, then I'm going to stick my neck out and say probably you can build a soft real-time system. That's not quite true, but it's reasonable. Okay, we're going to have a look at the module homepage apparently. Yeah, I think the idea of that is just to give you a view of what's coming up and what resources we've got. So this is for KF6010. Yeah. What's this like from the back? Can you see this slide? I wonder if I can blow it up a bit. What do we think now? Is that okay? So the program for semester 1 is available on the module page at the moment. In the lab this week, we're just going to have an introduction to the hardware and software development tools. Oh yeah, that's good. That's triggered off a little brain cell in my head to remind you that what we're going to be using some little embedded systems boards. If you haven't done a placement and you've come straight through from second year, you'll be familiar with them. It's the same FRDM K6010 boards that we used last year in second year. So these little ARM embed boards, they're now available for collection from the loans room. So the idea is that you'll borrow one of these boards for the year while you're taking this module. You need to bring it to the labs with you, but it means you can also take it home as well. In week 1, we'll show you how to set up the hardware and software development tools. So not only will you be able to use the boards in the lab, but you'll be able to configure your own computers to use the boards at home as well. So the loans room, I think, is open from, I checked this morning and I had an email confirming it. Definitely 9:30 to 16:30. I can't remember if that 9 was a 9 o'clock rather than a 9:30. But if you go between 9:30 and 4:30, you should find somebody in the loans room. Does everybody know where the loans room is now?
Yeah.
No? Okay, it's on the, it's, if you go to the end of this corridor, which floor are we on at the moment?
0.
We're on the ground floor. So if you go to the end of this corridor, before you get outside the building, turn right. The loans room is more or less opposite Castle's restaurant. Yeah? I can't remember the number. I think it's got something helpful like loans above the entrance to it. So down at the end of this corridor, on the right through the doors that lead to Castle's restaurant, the loans room is either the first or the second room on the left after you've done that. Yeah? So please make sure that you've picked up one of these boards before you come to your first lab session for this module. Have I gone on too long? I see people twitching and picking up their stuff. 1350, yes, okay. Yeah, all right, I can stop there. That's probably the key bit of information before you come to the lab. I'll tell you a little bit more about all this stuff in the labs. Just okay, has anybody got any last questions? Anything crucial that maybe you needed to have known that I haven't said? Okay, thank you very much. Cheers.